Okay, so have you ever wondered what holds atoms together? And you, before we start to think about, or as we start to think about that question, we'll just think about some of those fundamental forces that we know about in nature. We know about gravity. Gravity is what holds our solar system together. It's also, if you like, what keeps our feet on the ground. It's why when we jump up, a gravitational force due to the mass of the Earth attracts us back to the Earth, and that's why we don't sort of fly into space when we jump up. If you've ever fallen over, you're familiar, at least in a practical sense, with gravity. The second force, which I hope most of you are familiar with, is the electrostatic force. And that basically says that opposite charges attract and like charges repel. So two positive charges would repel each other, two negative charges would repel, a positive and a negative charge would attract each other. Now, magnetism is also related to charge and electrons. So it's a very similar sort of reasoning and logic to why we know that the opposite poles on a magnet attract, so a north and a south pole attract, but two north poles or two south poles will repel each other. Hopefully you've all played with magnets at some point and are familiar with it. They can either attract or repel each other. Now, if we think of a really, really simple atom like hydrogen, well, we can explain hydrogen sort of thinking about this because hydrogen has, let me just find the right pen. Hydrogen has simple hydrogen, one proton, that's all. So it has one proton in the middle with a positive charge, and surrounding that is one electron with a negative charge. And we know that opposite charges attract, so that electrostatic force basically keeps pulling the proton, keeps the proton and the electron keep pulling towards each other. But as it's spinning really fast, it basically just stays in orbit in the same way that the moon stays in orbit around the Earth, or the Earth stays in orbit around the sun. We'll do a whole topic on that sort of stuff later in the year if you've got questions on that. But basically there's this attractive force that allows it to keep spinning around and around. So for hydrogen, we can explain what holds the atom together, or for any atom, we can explain what holds the electrons spinning around the positively charged nucleus due to the protons because of the electrostatic force. But if you think about this a bit more deeply, why don't all positively charged protons in the nucleus repel each other and all atoms, except for hydrogen, basically explode? We'll take here this nucleus here. I haven't written the symbol, but hopefully you get two protons. Two protons is helium, so it's atomic number 2, helium. We've got two neutrons there, so mass number would be, 4, just jumped to the wrong thing. So what stops these two protons here? We know that like charges should repel. So these two things here should just push each other apart, and that atom basically should not exist. Why are those protons able to stay so close to each other? I'll let you think about that for a sec. Okay, any ideas? Well, there's a third fundamental force that we need to know about. So we know about gravity, we know about the electrostatic force. This next force is the strong nuclear force. And this is an attractive force between all nucleons, so that's protons and neutrons, that acts only over very, very short distances. That's a few nucleons in diameter. And remember, a proton or a neutron, like the nucleus of an atom, is very, very small compared to the overall size of the atom. If you think about that, how small is an atom video, I put the link up to earlier. So, the diameter of a nucleon is very, very small. And if you went equivalent to the distance, the diameter or the distance across 3 or 4 nucleons, that's basically as far as this strong nuclear force acts. So it's very, very strong at those short distances, but it gets weak really, really quickly. So at a very short distance, it's stronger than the electrostatic repulsion. So basically, if you think about that diagram that I just had on the previous page, for those 2 protons that are basically touching each other, the strong nuclear force is even stronger than the electrostatic repulsion, which is trying to push them apart. So that strong nuclear force is what holds the nucleus together. And it acts not just between protons, but it acts between protons and neutrons. And as we go on, we'll talk about this idea of neutrons almost, because they have this strong nuclear force, but there's no electrostatic repulsion, almost act a bit like a nuclear glue that helps hold the nucleus together. If we go to larger distances, the electrostatic force is stronger than the strong nuclear force, and the protons will repel each other. Let's have a look at this in a slightly more mathematical sense. So we'll just start with this diagram here. Firstly, if we try and push 2 protons too close together, firstly, the yellow dots represent 2 protons in each of these cases. The red arrow indicates the electrostatic force. The green arrow here indicates our strong nuclear force. And we're looking at basically the net or the total force between those 2. Now, if we actually try and push 2 protons too close together, so basically we try and squeeze them like squeezing 2 balloons together, so a distance less than their diameter, both these forces will be repulsive. So those things will both be trying to push each other away. So we can't basically squeeze 2 protons into each other. We're not so interested in that area, but that's sort of this area here at less than 1 diameter, nucleon diameter. Now, as we move out past that, we get to what we called the Goldilocks zone. I don't know if you remember the fairy tale about Goldilocks and the porridge and all that. But in this zone here, we have our 2 protons. The red force is the electrostatic, so that's trying to push away, but the nuclear force here is trying to hold them together, and that's stronger than the electrostatic, so that holds them together. So this is this area of the graph just in here. Nuclear force, attractive, electrostatic, repulsive. You add those 2 together, you get this zone where the nucleus will hold together. If they get too far away, like in this bottom case here, basically the electrostatic repulsion, it's weaker, but the nuclear force gets weaker faster, so the electrostatic repulsion is greater than the nuclear force holding together, so basically that would not be stable. That atom would want to explode, for lack of a better term. So as I've sort of done as we've gone through with the graph, we can think of an electrostatic force here, which is always decreasing and always repulsive. A nuclear force, which as long as we're less than 1 diameter apart, so we're not trying to squash them together, is always attractive, but gets weaker very, very quickly. This drops towards 0 much faster than the electrostatic force. If we add those 2 up, that shows that zone, sort of 1, 2, 3 and a bit nucleons in diameter, where the nuclear force is stronger than the electrostatic force, and we get an atom that will hold together. Hopefully that makes sense. That concept is probably a little bit new. It is a really important one. If you're struggling, maybe watch the video again, but if you're still not sure, definitely ask questions. Get me to talk about it some more. It is new and it is really important that we get our heads around this. Okay, let's move on to a consequence of that and look at stable and unstable nuclei. And we use the word nuclei we could also equally use the word isotope or atom. Is an atom stable? Is an isotope stable? Is a nuclei stable? When we use those three words, we really mean the same thing. And I'm probably going to be the worst culprit at switching between the two. So hopefully it doesn't confuse you too much. So firstly, for an atom to be stable, well, we've already talked about, we've got to have this case where the strong nuclear force that's holding it together is stronger than the electrostatic force that's trying to pull it apart. And as I hinted at before, neutrons have a really, really important role in helping this happen. Now, generally, most stable nuclei, so ones that will basically not fall apart at basically low atomic numbers, so the first few elements, so initially have a 1-to-1 ratio. So the number of neutrons is approximately equal to the number of protons. What we see is as the atomic number increases, we actually need a few more neutrons. So we need more neutrons than protons, and that's really because the neutrons are acting like as a glue and we're trying to put more and more like positive charges into that. So if you look at this graph, I haven't got neutrons on this axis, I've actually got mass number, but you can think 25 is the atomic number, 50 is the mass number. That means 25 protons, 25 neutrons. 50 protons, 50 neutrons. So even though I've got mass number here, you can sort of see that still indicates the ratio of neutrons to protons, because the mass number is just the sum of the two. I'll talk in lesson a little bit more about stable and unstable isotopes. On the previous slide, you'll see a link to the P-table website, which has some really good things, which I'll show you in class about how how you can research and find out about isotopes. I've also put a copy of just a little thumbnail of the periodic table that you'll often see in classrooms, which has this list of all these unstable isotopes. I've also put a link to that up on Teams. I can't, in this program, quickly jump back to that slide. That's why I haven't jumped back. But if you've got your notes in front of you, you'll see that in the bottom left-hand corner of the page, and I will show you that in class if we need to. So what the final thing it said that we needed to do is identify basically these areas where we get stable and unstable nuclei. Now, the first probably area that we need to think about is, why does this graph end here? And this graph ends here. If we were to put a number on that, it basically ends at 83. And the reason that we don't get any stable isotopes, we get isotopes but they're not stable that will eventually last forever, is because basically they just get too big. And the strong nuclear force can't overcome the electrostatic force between the protons at either end. So we're getting protons so far apart into that nucleus, they're into this sort of zone here, and eventually they are going to explode, for lack of a better term, and push each other apart, and that will make those atoms unstable. So in this zone above, we say Z greater than 83, they're just too big. There's no stable ones there. The other problem that we can have, and we're going to explore this in more detail in the next subtopic, so at the moment all we just need to be familiar with is that this is an unstable zone. If we go in this zone, let's use a highlighter pen. That's a rubber highlighter pen. I think that's blue. Yeah. In this zone here, above that line, we would basically have, sorry, I'm just struggling here with pens. We would have too many neutrons. Basically, an atom doesn't want to have too many neutrons. It doesn't want to have too much glue, and that will make it unstable. And we're going to learn about what happens next week with those sort of atoms. And then in this area down here, basically, we have too few neutrons. So we effectively don't have enough of those neutrons providing that strong nuclear force to hold the atom together, and these atoms will also be unstable. So they are, if you like, the three zones. Above the line, too many neutrons. Below the line, too few neutrons. Greater than 83. So out here on the right-hand side, just too big. So I might just finish off by going back to that previous slide and just checking off that we've covered everything that we should have. Okay, so here's the links to the P table, which can show us stable and unstable isotopes, which we'll have a look at in class. Here is the thumbnail of that periodic table, and you may have one like this up in your lab, and you'll see a list up here of all the unstable isotopes. There's a copy of this high definition, high resolution copy of this already up on Teams. So just quickly checking, do we know the nucleus is held together by a strong attractive nuclear force? Hopefully we know that. Describe the properties of the strong nuclear force, including its short range. So it's attractive, only acts over very short distances. Describe the balance between the electrostatic force and the strong nuclear force in stable nuclei. Basically, the strong nuclear force is stronger than the electrostatic force, which is trying to push them apart. Attraction, stronger than repulsion, so it holds together. Use the properties of the electrostatic force and the strong magnetic force to explain why some isotopes are unstable. Basically, above 83, which is the most important one in terms of this point, the nucleons, or in this case the protons, become so far apart within the nucleus that the strong nuclear force cannot counteract the electrostatic repulsion. Locate stable and unstable nuclei on an N versus Z graph. Now, N is the number of neutrons. I prefer to do it in terms of mass number, which I explained as we went through that slide. Z is the atomic number. So hopefully we are confident that we understand what's happening with all of this science understanding, or if you like, we can demonstrate all of these success criteria if we want to use the current day lingo that teachers like to use. Cheers, and that's it for the nucleus subtopic.